Well, so I'll use those firecrackers. You bet. All right. Anyway, here we got this junk to deal with. Okay, 5 trips, Sabrina. Here, come on. Come on. Come on. I'll put these firecrackers I found in here for a little later. Guess what we're going to do with these? Guess what we're going to do with the firecrackers, Sabrina? Guess what? Firecrackers. Schrodinger's equation. Yeah. Schrodinger's equation. Yeah. Hey, so you know what? Today, when we went and did that thing, we found these firecrackers. A perfect thing for April Fool's Day. Foolish stuff on April Fool's Day. Not really foolish. Firecrackers aren't really foolish. I mean, they kind of are. But anyway, there they are. There they are. There it is. There they are. Firecrackers. I found them. They've been in the rain, and they're all in an entangled state. Perfect for, guess what? Schrodinger's equation. First, we have laws of probability. Okay, are they any good or not? That's the question. A or B. That's the question. That's the first equation. Are they any good? We can pick one and we can check it as an equation and collapse it and be minus 1 firecracker, right? Minus 1 firecracker and find out if they work, okay? Right? And then what does that say about them? That says that there's a probability that they all work. They're in an entangled state. So there's a probability, right? But we're not sure, so we have to apply. So we have to ask a guy named Heisenberg. Heisenberg's uncertainty principle. Yeah. So what do you think? Right now, it's a 50-50 possibility that they work. There's an uncertainty. I'm going to set these firecrackers off. And one of them, we're going to set one off right out the gate. And check our probability. We're also going to do it, and guess what? A time tunnel. These 2 mirrors are about 1 meter apart. As close as I can get them with what I've got to work with to set up. Later I'll set up an actual scientific time tunnel where there will be exactly 1 meter apart. And exactly 1 meter apart, what happens is that light bounces back and forth 299 million some odd times in 1 second. Okay? And as a sound, as it goes off, the sound is going to bounce back and forth at 1,000 times, because it's about 1,000 meters a second in sea level for sound. So 1,000 times for the sound and 299 million times for the light. Okay, there it is. There's a firecracker. Checking the probability. Here we go. And of course, we're going to do this in grand April Fool's Day style. We got this and that. Woo! So we're going to try to light this. with this thing. Ooh, we did it. Ooh, 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 ooh. Oh! Okay, well, it was a good firecracker. So we've reduced our we have reduced our level of doubt. We could say it's pretty good probability now that the rest of these firecrackers are good. Okay, now here comes the twin cat paradox. So this is how this works. See, we've got two firecrackers. There's one here, and there's one here. Now, because they've been in the rain, they're both in an entangled state. They both have the same probability of not working. Okay. Now, because Shrodinger says that if one worked, the others will probably work. If two works, well, you know what's going to happen is they're in an entangled state. We're going to have action at a distance. That's how that's going to work. When we light the one, we light them both at the same time. When we collapse the equation, that they are entangled, okay, in the same state. In other words, they're both working. They've been in the rain the same length of time. All right, here, let's see if we can get them light. We're going to collapse the equation right now with our flame on. Whoa, okay, we got one, and the other one didn't. See, there's our probability. And that one may go still. Here, let's try to light this one now. Okay, so we collapsed that equation. How do you like that one? It's burning like a candle. I'd say that one's a dud. No, yeah, is it a dud? Yeah. It's a dud. Okay. All right, let's do it again. Let's set her up and do her again. We got some other foolish experiments we're going to show you too. We got a gyro experiment we're going to show you in a little bit. Okay. And on that gyro experiment, we want to make sure, absolutely sure. Okay. All right, here we go. Okay, here we go. That one's a dud. See, we had a similar result. So we've had twice we had the same result. Out of the two, one was live and the other one was dead. What about that? Let's do it one more time, huh? Then we're going to save some of these for another little experiment we're going to do. All right, here we go. One there. Here on this little pedestal. Okay. All right, here we go. Oh, we got two of them. Fire. All right, cool. All right, so out of 3 tries with 2 at a time, we had 2 that were opposite and 1 that was the same. Whoa! Okay, that was kind of fun. We'll just put these away. tucked away for later. So, what does that say? Yeah, whoa, there she is, my baby. Okay, so what does that say? We had, out of 2 single tests, 1 was bad and 1 was good. So, basically the first test we had, well, I know, actually the 2 tests, basically, you can think of it in percentages. 8 equals 100, if 8 equals 100%, right? 4 would equal 50%. 3. 5 is 1/2 of the way between 4 and 3. If 8 equals 100, 4 equals 50, 5 is going to equal half of that. Halfway to. Well, because 75% would equal, would be, right? Isn't that right? See, because if, or 25% would be 2. 50% would be 4. 60% would be 6. 75% would be 6. Okay? 100% would be 8. Okay? And it's a 3 to 5 ratio, or 3 and 5. So, 6 is more than 75%, and 4 is 50%. So you're halfway, right in between 50 and 75%. So half of 25 is 12 and a half. So you take 50 plus 12 and a half is 62.5%. Okay? There you go. That's kind of a roundabout way to figure that out, but it works. And I did it without a calculator.